As vast as the universe already is, scientists continue to tell us that it is expanding. But what does that really mean? When we think of expansion, we might imagine objects moving apart in space. However, in this case, it's not just the objects. Space itself is stretching. Galaxies are drifting away from each other, not because they are traveling through space, but because the very fabric of space between them is growing. If the universe is truly expanding, what exactly is it expanding into? Is there something beyond it? Or is space itself boundless? Join me as we explore these questions. In the early 20th century, most scientists believed the universe was static and unchanging. The prevailing thought was that the universe had always existed as it was, with galaxies and stars remaining in fixed positions. However, this perspective began to shift when astronomers closely examined distant galaxies. One of the most influential figures in this transformation was American astronomer Edwin Hubble. His observations would completely reshape our understanding of the cosmos. Working at the Mount Wilson Observatory in California, Hubble used the powerful 2.5-meter Hooker telescope, the most advanced telescope of its time, to study faint celestial objects. Initially, it was unclear whether these objects were part of the Milky Way, or if they were independent galaxies. Hubble was able to confirm that many of these faint patches of light were actually entire galaxies far beyond our own. As he continued his research, Hubble made a remarkable discovery. When analyzing the light coming from distant galaxies, he observed a shift toward the red end of the spectrum, a phenomenon known as redshift. This occurs when light waves are stretched, causing them to appear redder. It's similar to the Doppler effect, where the pitch of a siren changes as it moves away, except in this case, it's light being stretched rather than sound. Hubble's observations revealed that galaxies were not stationary, they were moving away from us. He didn't just see this in a few galaxies, he noticed a consistent pattern. The farther away a galaxy was, the greater its redshift, meaning it was receding faster. This discovery led to what is now known as Hubble's law. This groundbreaking revelation demonstrated that the universe wasn't static but expanding. If galaxies are moving apart, it implies that in the past they must have been much closer together. This realization led to the idea that the universe had a beginning, a moment when all matter and energy were condensed into a tiny, incredibly dense state before expanding outward. This concept formed the foundation of what we now call the Big Bang Theory. Hubble's discovery revolutionized not just astronomy, but our entire perception of the universe. His findings overturned the notion of an eternal, unchanging cosmos and introduced a dynamic view, one in which the universe has been expanding ever since its birth. When we talk about the expansion of the universe, it doesn't simply mean that galaxies are drifting apart through space. It's not as if they are moving through an empty void like ships sailing across an ocean. Instead, the space between them is actively stretching. A useful way to visualize this is to imagine the universe as a balloon. If you draw dots on its surface to represent galaxies, as the balloon inflates, the dots move farther apart. However, they are not traveling across the surface itself is expanding. This is similar to what happens in our universe. This concept changes how we think about space. We often picture space as a fixed stage, where planets, stars, and galaxies exist and move. But in an expanding universe, space itself is dynamic. It is constantly growing. One fascinating consequence of this expansion is that the farther away a galaxy is, the faster it appears to be moving away from us. This happens because more space is expanding between us and that distant galaxy. As a result, some galaxies are so far away that their light will never reach us. The space between us is expanding so rapidly that their light is essentially being carried beyond our observable horizon. This means that although the universe is filled with galaxies, there are parts of it that we will never be able to see or explore. These regions lie beyond what we call the observable universe, the portion of the cosmos from which light has had enough time to reach us since the universe began. Interestingly, this cosmic expansion does not affect everything equally. Objects that are bound together by gravity, such as the Earth and the Sun, or even entire galaxies, remain unaffected. The expansion only becomes noticeable at vast distances, between galaxies that are not gravitationally bound. Another key point about this expansion is that there is no central point from which everything is expanding. No matter where you are in the universe, it will appear as though all other galaxies are moving away from you. This challenges our everyday way of thinking, where we expect motion to occur relative to a fixed background. But in the universe, the background itself is stretching. The story of cosmic expansion doesn't begin with a slow, steady stretching of space. Right after the Big Bang, the universe underwent an incredibly rapid phase of expansion known as inflation. During this brief but intense period, lasting only a fraction of a second, the universe expanded at an astonishing rate, far faster than its current pace. In that tiny moment, space grew from a minuscule point to a vast expanse spanning light years. Inflation played a crucial role in shaping the universe as we see it today. It smoothed out irregularities, making the cosmos remarkably uniform while also creating tiny fluctuations in density. These fluctuations later became the seeds of galaxies, stars, and planets. Without inflation, the universe may never have developed in a way that could support life. After the inflationary period ended, the expansion of the universe continued at a slower rate. However, in the late 1990s, scientists made a shocking discovery. Not only is the universe still expanding, but the rate of expansion is actually accelerating. This was unexpected. Scientists originally thought that gravity would gradually slow the expansion down over time. Instead, observations of distant supernovae revealed that galaxies were moving apart at an ever-increasing rate. This led to the discovery of a mysterious force known as dark energy. Dark energy is thought to make up about 70% of the universe's total energy, yet its nature remains largely unknown. Unlike normal matter or even dark matter, dark energy does not cluster together. It appears to be evenly spread throughout space, influencing the universe on a grand scale. One possibility is that dark energy is a fundamental property of space itself. If this is the case, as space expands, more dark energy comes into existence, causing expansion to accelerate even further. Another idea suggests that dark energy might be related to the cosmological constant, an idea originally introduced by Albert Einstein. At first, Einstein included the cosmological constant in his equations to keep the universe static, believing it to be unchanging. When Hubble discovered the universe was expanding, Einstein dismissed the constant as his biggest blunder. However, with the discovery of dark energy, some scientists now think this concept may have been onto something. The presence of dark energy raises profound questions about the universe's ultimate fate. Will it continue expanding indefinitely, leading to a cold, dark, big freeze, where galaxies become isolated and stars burn out? Or could expansion accelerate so much that it eventually rips apart galaxies, stars, and even atoms in a big rip? These are open questions that remain at the forefront of cosmology. The expansion of the universe has not always been at a uniform rate. Over billions of years, the rate at which space stretches has varied. Right after the Big Bang and the inflationary period, expansion was incredibly rapid. After inflation ended, gravity played a role in slowing down the expansion, at least for a while. However, with the discovery of dark energy, it became clear that expansion is now speeding up once again. Understanding the universe's expansion rate is one of the most critical challenges in modern cosmology. Scientists continue to refine their measurements, seeking to unravel the mysteries of dark energy and the fate of the cosmos. A fundamental value in cosmology, known as the Hubble constant, describes the rate at which galaxies are moving away from each other based on their distance. This constant is crucial because it helps scientists estimate the universe's age, size, and future expansion. It is measured in kilometers per second per megaparsec, where a megaparsec is a unit of distance used by astronomers, equivalent to approximately 3.26 million light years. In simple terms, if a galaxy is 1 megaparsec away, the Hubble constant indicates how fast it is receding from us in kilometers per second. The greater the distance of a galaxy, the faster it is moving away, and the Hubble constant quantifies this relationship. Determining its value requires precise measurements of both the distances to galaxies and their velocities. One of the primary methods for measuring cosmic distances involves using a special type of star known as a Cepheid variable. Cepheid variables are stars that periodically grow brighter and dimmer, following a predictable cycle. The key feature of these stars is that the time it takes for their brightness to fluctuate is directly linked to their true luminosity. By comparing their intrinsic brightness with how bright they appear from Earth, astronomers can accurately calculate their distance. Once the distance to a galaxy is established, its speed can be determined by measuring the redshift of its light. As galaxies move away, their light stretches into longer, redder wavelengths. The degree of redshift provides clues about the galaxy's velocity. With both the distance and velocity of galaxies in hand, astronomers can calculate the Hubble constant. While the basic idea behind this measurement is straightforward, pinpointing its exact value has proven to be challenging. Over the years, different research teams have reported slightly varying results, leading to a scientific debate known as the Hubble tension. This refers to the discrepancy between two primary methods used to determine the Hubble constant. The first method involves direct observations of galaxies, utilizing objects like Cepheid variables and supernovae as distance markers. This approach, which relies on relatively nearby galaxies, suggests a Hubble, constant of approximately 73 kilometers per second per megaparsec. The second method derives its estimate from observations of the early universe, particularly the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. By analyzing patterns in the CMB, scientists can infer the universe's expansion rate shortly after its formation, and use theoretical models to estimate the Hubble constant today. However, this method yields a slightly lower value of around 67 kilometers per second per megaparsec. Although this difference between these two measurements may seem small, it is significant enough to suggest that something might be missing from our current cosmological models. If our understanding of the universe's expansion were complete, both methods would produce the same result. This discrepancy raises the possibility that an unknown aspect of physics has yet to be discovered. One potential explanation is that dark energy, the mysterious force driving the universe's accelerated expansion, does not behave exactly as scientists currently assume. If dark energy has properties that are not yet fully understood, it could influence the expansion rate in unexpected ways. Another possibility is the existence of an unknown form of matter or energy that has yet to be detected, which could have affected the early universe differently than it does today. Another intriguing idea is that gravity might behave differently over vast cosmic distances. Einstein's general theory of relativity has been highly successful in describing how gravity functions on smaller scales, such as within our solar system and galaxies. However, its behavior across the largest cosmic structures has not been directly tested. If gravity operates slightly differently on these scales, it could impact the expansion rate and explain the discrepancy in the Hubble constant measurements. Some scientists have proposed modifications to general relativity to account for this possibility. Complicating matters further, there's also the question of whether the Hubble tension is a real physical issue or simply a result of measurement errors. Determining distances in space is incredibly challenging, and even small inaccuracies in observations could contribute to the discrepancy. For example, uncertainties in how we interpret the brightness of Cepheid variables or supernovae could introduce errors into distance calculations. Similarly, the analysis of the cosmic microwave background depends on complex theoretical models of the early universe, and any miscalculations in these models could affect the predicted value of the Hubble constant. As the universe has evolved over billions of years, its expansion rate has changed. In the early universe, gravity played a significant role in slowing down expansion, as galaxies were closer together and their mutual gravitational attraction was stronger. However, around 4 billion years ago, the expansion began accelerating due to the influence of dark energy. With the development of new technologies, astronomers hope to refine their measurements and resolve the Hubble tension. Cutting-edge telescopes, such as the James Webb Space Telescope, are providing more precise data that may bring us closer to a definitive answer about the true value of the Hubble constant. The expansion of the universe raises important questions about how gravity, one of the fundamental forces of nature, interacts with the stretching of space on the largest scales. While galaxies move apart due to cosmic expansion, gravity keeps objects like stars, planets, and even galaxy clusters bound together. This dynamic interplay between expansion and gravity shapes the structure of the cosmos in ways that can seem contradictory. According to Einstein's general relativity, gravity is the force that pulls objects toward one another. It governs planetary orbits, the formation of galaxies, and the clustering of galaxies into larger structures. Without gravity, the universe would be a chaotic expanse of scattered matter, rather than the structured cosmos we observe today. Gravity works because mass bends the fabric of space-time, creating an attractive force. The more massive an object, the stronger its gravitational pull. At the same time, the universe is expanding, with space itself stretching and carrying galaxies along with it. However, this expansion is only noticeable on extremely large scales. Within galaxies and galaxy clusters, gravity dominates, effectively counteracting the effects of expansion. The gravitational pull within these structures is strong enough to keep them intact, which is why galaxies do not expand along with the universe. For example, the Milky Way and the Andromeda Galaxy are not drifting apart due to cosmic expansion. Instead, they are actually moving toward each other, pulled together by their mutual gravitational attraction. This illustrates how gravity can override cosmic expansion in regions where it is strong enough. Similarly, galaxy clusters, massive groupings of hundreds or thousands of galaxies, are held together by gravity, even as the space between different clusters continues to expand. Over time, this expansion will drive galaxy clusters farther apart, but within each cluster, gravity keeps galaxies bound together. If the universe's expansion continues to accelerate due to dark energy, some scientists speculate that gravity may eventually lose its grip even on galaxies and galaxy clusters. In a hypothetical scenario known as the Big Rip, Dark energy could become so dominant that it would tear apart galaxies, solar systems, and even atoms themselves, ultimately leading to a universe of total isolation and emptiness. Another key factor in this balance of forces is dark matter, an invisible substance that does not interact with light, but exerts a strong gravitational pull. Dark matter plays a crucial role in holding galaxies together, as their visible matter alone would not provide enough gravitational force to prevent them from dispersing. Without dark matter, galaxies would be more susceptible to cosmic expansion, making it an essential component in the cosmic balance between gravity and expansion. As we observe the universe, we are essentially looking back in time. The light from distant galaxies takes millions or even billions of years to reach us, meaning that the farther away we look, the older the light we see. However, there is a limit to how far we can observe. This boundary is known as the cosmological horizon. Beyond this horizon, galaxies are moving away so rapidly due to the expansion of space that their light can never reach us. While nothing can travel faster than light through space, space itself can expand at any rate, carrying galaxies beyond our observable reach. As a result, there are regions of the universe we will never be able to see, placing a fundamental limit on how much of the cosmos we can explore. Beyond this boundary, light from distant celestial bodies has not had sufficient time to reach Earth, making these regions inaccessible to our observations. This limit is often called the observable universe, but it does not signify the end of the cosmos. Instead, it represents the furthest extent of what we can perceive. Countless galaxies, stars, and cosmic structures likely exist beyond this horizon, yet they remain invisible to us because their light has not had enough time to travel across the vast expanse of space. The observable universe is merely a fraction of the entire cosmos. Even if we wait for billions of years, we may never see beyond this boundary due to the accelerating expansion of the universe. As space continues to expand, the observable universe is constantly changing. New regions become visible as light from farther away reaches us. However, due to the acceleration of cosmic expansion, some galaxies that are currently within our view may eventually slip beyond our reach. Their light will stretch and redshift until it becomes undetectable. This paradoxical reality means that although the observable universe grows over time, the number of galaxies we can actually observe may decline. We are limited to studying only what falls within this observational horizon, meaning our understanding of the universe is confined to the light that has already reached us. Yet, since the universe is far larger than what we can see, an immense amount of information remains beyond our grasp. Hidden galaxies, cosmic structures, and potentially even unknown regions of the universe that will forever remain out of reach. Several factors define the cosmological horizon, one of the most crucial being the age of the universe. The cosmos is approximately 13.8 billion years old, and because light has a finite speed, we can only observe objects whose light has had enough time to travel to us. This means the most distant objects we can currently detect are about 13.8 billion years old. However, due to the continuous expansion of space, the actual distance to these objects is much greater than 13.8 billion light years. In fact, the present estimated boundary of the observable universe is around 46 billion light years away. While this may seem contradictory, it aligns with the nature of a cosmic expansion. As light travels toward us, the space between us and these distant galaxies stretches, increasing their current separation from us. The cosmological horizon defines the limit of our observations, but it does not indicate the edge of the universe. Beyond this boundary, the universe most likely continues indefinitely, though we have no direct way to observe or interact with it. The question of what exists beyond the observable universe has fascinated scientists for decades, leading to numerous theories and speculations. One straightforward hypothesis suggests that the universe extends much as it does within our observable region. This idea is based on the principle of cosmological homogeneity, which posits that on very large scales, the universe appears roughly the same in all directions. If this assumption holds, then beyond the observable universe, we would find more galaxies, stars, and cosmic structures similar to those we already see. In this view, the observable universe is just a small piece of a far larger whole. However, some scientists theorize that the universe beyond our horizon may not be uniform. While the observable universe appears relatively smooth on vast scales, there could be variations in the density of matter and energy beyond our line of sight. Some regions may be packed with more galaxies, while others could be relatively empty. Though we cannot directly see these differences, they could have significant implications for our understanding of cosmic structure. A more exotic theory proposes that our universe is part of a vast multiverse. According to some interpretations of cosmic inflation theory, our observable universe could be just one of many pocket universes, or cosmic bubbles, formed in the early moments of inflation. In this scenario, space expanded rapidly, creating separate regions of space-time, each with its own distinct physical properties. Our universe would be just one such region, while others remain beyond our observational reach. If this multiverse theory is correct, the universes beyond our horizon could differ drastically from our own. They might have entirely different physical laws, varying fundamental constants, or even additional dimensions. While this concept is speculative and challenging to test, it provides a fascinating perspective on what could exist beyond our observable universe. Even if we assume that the universe beyond our horizon is similar to what we can see, cosmic expansion continues to shape these distant regions. As space stretches, galaxies beyond our reach move further away, increasing the separation between them. This means that even in the most distant realms, cosmic expansion is still at work, influencing the evolution of space over time. In the far future, regions beyond the observable universe may become even more isolated from what we can detect. If the expansion of space, driven by dark energy, continues to accelerate, vast portions of the universe may move beyond the reach of light, effectively severing connections between different cosmic regions. In such a scenario, the universe could become increasingly fragmented, with immense voids of empty space separating distant pockets of galaxies. These regions would still exist, but they would be forever cut off from one another, unable to exchange energy or information. For any potential observers in these distant regions, the universe would appear much smaller and more isolated as time passes. The accelerating expansion of space ensures that eventually much of the cosmos will slip beyond our ability to perceive it. The cosmological horizon is an ultimate limit, one we cannot cross. While we can speculate about what lies beyond, we may never be able to confirm these ideas through direct observation. The ongoing expansion of the universe raises profound questions about the nature of space itself. Does space extend infinitely, or is it expanding into some larger framework? This question goes beyond mere cosmic expansion and delves into the very nature of space and time. If the universe is infinite, then it has no edge and no boundary. It stretches endlessly in all directions. In this case, the expansion of the universe means that even though space is limitless, the distances between objects within it continue to grow. No matter how far one travels, space continues without an endpoint. This concept is difficult to comprehend because we are accustomed to thinking about things that have physical limits. However, in an infinite universe, there would be no outer edge. Alternatively, some theories propose that the universe is finite but unbounded. This would mean that while space has a finite size, it does not have a definite boundary. A helpful analogy is the surface of a balloon. While the surface is finite, it has no edges. If you traveled in a straight line long enough, you would eventually return to your starting point. The universe could behave similarly, being finite yet without an outer boundary. Another possibility is that the universe is expanding into something larger. However, this idea is misleading. When objects expand, we typically think of them growing into a larger pre-existing space. But in the case of the universe, space itself is expanding, not expanding into something. Space and time are intrinsic parts of the universe, meaning that if there is something beyond, we have no way of knowing what it might be. If our universe exists within a greater multiverse, then its expansion could be occurring within a larger cosmic framework. However, even in this case, our universe's expansion does not require an external space to expand into. At extremely small scales, space itself is thought to be anything but smooth. Quantum mechanics suggests that the fabric of space-time is a dynamic, ever-changing landscape known as quantum foam. This quantum foam represents tiny fluctuations in energy at incredibly small scales, where quantum effects dominate. In this realm, space behaves unpredictably, with particles appearing and disappearing in fractions of a second. Could the universe be infinite at large scales, but fundamentally granular at the smallest levels? If so, the concept of infinite space becomes even more complex. While cosmic expansion operates on vast cosmic distances, quantum fluctuations occur at minuscule scales. Some scientists speculate that there might be a connection between these two extremes. Perhaps the very expansion of space is influenced by quantum processes at the smallest scales. This remains an active area of research, as scientists strive to unify quantum mechanics with our understanding of cosmic expansion. The idea of curved space originates from Einstein's general theory of relativity, which describes how massive objects like stars and galaxies distort the space around them, creating what we perceive as gravity. On small scales, such as within our solar system, this curvature is barely noticeable. However, on cosmic scales, the universe's overall curvature can take one of three possible forms: flat, closed, or open. The shape of the universe is determined by the total amount of mass and energy it contains. A flat universe implies that space extends infinitely in all directions without bending back on itself. In this case, parallel lines will always remain parallel, and the angles in a triangle will sum to 180 degrees, much like they do on a flat sheet of paper. A universe with this geometry has just the right balance of mass and energy to prevent it from either collapsing under its own gravity or expanding endlessly at an increasing rate. In a closed universe, space bends in on itself, resembling the surface of a sphere. If one were to travel far enough in a straight line, they would eventually return to their starting point. The total mass and energy in a closed universe would be high enough for gravity to eventually halt expansion, causing the universe to contract and culminate in a big crunch, where all matter and energy are drawn back together. Conversely, an open universe has a negative curvature, similar to the shape of a saddle. In this scenario, space would continue expanding indefinitely, with galaxies moving farther apart at an ever-increasing pace. The universe would not contain enough mass and energy to pull itself back together, meaning its expansion would never cease. In an open universe, the angles of a triangle would sum to less than 180 degrees, and parallel lines would gradually diverge. To summarize, in a flat universe, expansion slows down over time due to the gravitational influence of its mass. In a closed universe, expansion halts and reverses, leading to a collapse. In an open universe, expansion persists indefinitely, though it slows down over time. One of cosmology's central objectives has been to determine the universe's actual shape. By analyzing the cosmic microwave background, CMB, scientists have measured large-scale space curvature and found that the universe appears to be remarkably flat. This does not necessarily mean it is perfectly flat, but rather that any curvature is extremely small, so small that our current instruments cannot detect it. However, even in a flat universe, expansion does not necessarily proceed at a constant rate. The discovery of dark energy has transformed our understanding of cosmic evolution. Dark energy is causing the universe's expansion to accelerate, regardless of its curvature. Even if the universe is geometrically flat, dark energy could drive an ever-accelerating expansion, causing galaxies to move apart at increasing speeds. If the universe is indeed flat, as current observations suggest, this implies that the total density of mass and energy is very close to a critical value. Any slight deviation from this balance would have resulted in a universe that was either open or closed. This raises an important question. Why is the universe so close to this critical density? The theory of cosmic inflation provides a possible explanation. According to this idea, the universe underwent an extremely rapid expansion in its earliest moments, stretching out any initial curvature and leaving it nearly flat on large scales. Although our universe appears flat, subtle effects of curvature may still exist in ways we have yet to understand. On smaller scales, such as within galaxies or galaxy clusters, the effects of gravitational curvature are very real. The immense gravitational influence of massive objects bends space, distorts light, and affects planetary motion. It is also possible that the universe possesses a slight curvature that remains undetectable with current technology. If it is slightly open or closed, the effects would be too minor to observe directly. Future advancements in measurement techniques and observational tools may eventually reveal more about the universe's true shape and how it relates to cosmic expansion. As the universe expands, distant galaxies are moving away from us at an accelerating rate. This expansion, driven by dark energy, means that galaxies far from our own are receding at ever-increasing speeds. Eventually, they will be moving away so quickly that their recession velocity will exceed the speed of light. At first, this may seem to contradict the laws of physics, which state that nothing can travel faster than light. However, it is not the galaxies themselves that are moving faster than light. It is space itself that is stretching, carrying them along. This distinction is crucial to understanding what happens to these distant galaxies. As space expands, the light from these galaxies must travel increasingly longer distances to reach us. Eventually, the expansion of space will outpace the ability of light to traverse it, causing these galaxies to disappear from our view. They will still exist, but they will be beyond our observational reach, effectively isolating us within a shrinking observable universe. Even now, some galaxies are on the verge of vanishing from our view. Over time, as they continue receding, their light will become stretched into longer wavelengths due to redshift. Eventually, this light will be stretched so much that it will move beyond the visible spectrum, becoming undetectable even with the most advanced telescopes. In the distant future, billions of years from now, most galaxies will have moved beyond the cosmic horizon, the limit of the observable universe. The only galaxies that will remain visible will be those gravitationally bound to our own, such as those in our local group, including the Milky Way and Andromeda. Since gravity keeps these galaxies together, they will not be affected in the same way by cosmic expansion. Instead, they will eventually merge into a single massive galaxy. Beyond the small cluster, the rest of the universe will fade into darkness. As more galaxies cross the cosmic horizon, the observable universe will appear emptier and lonelier. Future astronomers, billions of years from now, may not have any evidence that other galaxies ever existed, as all traces of them will have vanished beyond the cosmic horizon. In the distant past, galaxies frequently collided and merged, triggering bursts of star formation and shaping cosmic structures. However, as expansion continues, these interactions will become increasingly rare. The universe will grow more isolated, with fewer opportunities for galaxies to influence one another. Eventually, even the stars within our galaxy will burn out. The universe will become darker and colder as stellar formation slows and existing stars die. This era, known as the heat death of the universe, marks a state where expansion has progressed so far that the cosmos can no longer sustain the dynamic processes that once defined it. As the universe expands at an accelerating rate, some scientists have wondered whether this process could influence the fundamental laws of physics. Traditionally, physical constants such as the speed of light, the strength of gravity, and the fine structure constant, which governs electromagnetic interactions, are assumed to remain fixed. However, some theories propose that these values might shift over time. These constants define how the universe operates. The speed of light sets a fundamental limit on how fast information and objects can travel. The gravitational constant determines the strength of attraction between massive objects. The fine structure constant affects atomic interactions and the behavior of light. If any of these values were to change even slightly, the universe would behave very differently. For example, a slight variation in the strength of gravity could impact star formation, galaxy evolution, and even the fundamental structure of atoms. Some researchers have suggested that certain constants may have been different in the early universe. Observations hint that the fine structure constant might have varied slightly billions of years ago, though this remains controversial. If true, this would imply that cosmic expansion does not merely alter the arrangement of galaxies, but may also influence the fundamental laws governing reality. While no definitive evidence has been found for changing constants, continued observations and experiments may one day reveal whether the fabric of physics itself evolves as the universe expands. The expansion of the universe, or potentially other cosmic processes, could subtly impact the fundamental constants of nature. If dark energy behaves in ways that remain unclear to us, it might introduce slight variations in the fundamental forces that govern the cosmos. Some theories propose that dark energy could be intrinsically linked to the evolution of the universe, affecting these constants over time. The stretching of space due to cosmic expansion might also influence how we perceive time. As distances between objects increase and light wavelengths elongate, could the same spatial expansion alter the fundamental nature of time itself? Some more speculative ideas suggest that cosmic expansion not only affects the constants of nature, but could eventually give rise to entirely new physical laws. According to certain hypotheses, as the universe continues to expand and cool, high-energy processes might shift into new states, causing fundamental forces to change in ways beyond our current comprehension. This scenario could lead to phase transitions in the universe, where physical laws reorganize under different conditions, much like water freezing into ice at specific temperatures. If such transformations occur, the universe as we know it could undergo radical changes over billions or even trillions of years. As the universe expands, the large-scale structures that define it are constantly reshaped. These structures, galaxy clusters, filaments, and vast cosmic voids, form as gravity pulls matter together over billions of years, creating an intricate web of galaxies connected by dark matter and ordinary matter. However, while gravity works to bind these structures, cosmic expansion counteracts it, pulling galaxies apart and creating a delicate balance between attraction and separation. Over time, this expansion increases the gaps between cosmic structures, stretching the fabric of the universe and altering its large-scale shape. The universe is structured in a vast, web-like arrangement known as the cosmic web, composed of long filaments of galaxies that connect dense galaxy clusters. Between these clusters and filaments lie immense voids, regions where very few galaxies exist. However, the expansion of space is not uniform. While galaxies within clusters remain gravitationally bound, the space between these clusters continues to expand, causing the voids to grow larger and the filaments to stretch. As this process unfolds, galaxies within the filaments are gradually pulled apart, a phenomenon known as cosmic drift. Once relatively close neighbors, these galaxies become increasingly isolated over time. This growing separation reduces the frequency of galaxy interactions, including mergers and gravitational exchanges, which were far more common in the universe's early history. The expansion of space effectively silences the cosmic landscape, making such events increasingly rare. One of the most striking consequences of expansion is the enlargement of cosmic voids. These vast empty regions between galaxy clusters are expanding, pushing galaxies farther apart and fragmenting the large-scale structure of the universe. In the distant future, these voids will dominate the cosmos, with galaxy clusters appearing as isolated islands in an ever-expanding sea of emptiness. Within galaxy clusters, gravity is strong enough to counteract cosmic expansion, keeping the galaxies gravitationally bound. However, beyond these clusters, expansion is relentless. While galaxy clusters remain connected by cosmic filaments today, these connections will weaken over time as space stretches, eventually pulling galaxies apart to the point where filaments can no longer hold them together. The clusters themselves will persist, bound by their own gravity, but the distances between them will continue to grow. As voids expand, fewer galaxies will be visible from any given vantage point in the universe. The light from distant galaxies will be stretched and redshifted beyond detectability, effectively reducing the number of observable galaxies. In the far future, an observer in any galaxy may only be able to see the galaxies within their own local cluster, with the rest of the universe fading beyond the cosmic horizon. The processes that once shaped galaxies, such as mergers, star formation, and material exchange, will slow as the universe ages. In the early universe, galaxies formed through the collapse of gas and dark matter within dense regions of space. However, as the universe expands, the overall density of matter decreases, making it increasingly difficult for new galaxies to emerge. While existing galaxies will continue evolving, the formation of new ones from primordial gas clouds will become exceedingly rare. Eventually, the universe may reach a stage where no new galaxies form, leaving the existing ones to drift further apart, creating an ever darker and quieter cosmos. Time and space are deeply intertwined within the fabric of the universe, leading to speculation about whether cosmic expansion could influence the passage of time itself. While time is often perceived as a constant, unchanging forward march, the relationship between space, time, and the universe's expansion suggests that time might not be as rigid as it appears. According to Einstein's theory of general relativity, time and space form a single entity known as space-time. This means that any changes to space, whether bending due to massive objects like stars or stretching from cosmic expansion, can also have an impact on time. As the universe grows, distances between objects increase and the very structure of space-time expands, but does this stretching alter the flow of time? On human timescales, the answer appears to be no. Our clocks tick at a steady rate. Earth orbits the sun predictably, and the passage of days and years remains consistent. Locally, the influence of expansion is negligible because gravity dominates small-scale structures, keeping planets, stars, and galaxies intact. However, on cosmic scales, where vast distances separate galaxies, the relationship between time and expansion becomes more complex. As space expands, light traveling across it is stretched, leading to the redshift we observe in distant galaxies. This stretching doesn't just affect light waves. It also influences our perception of time. Light from distant galaxies doesn't merely appear redder, it also arrives more slowly. The farther away a galaxy is, the more time appears to slow down from our perspective. This effect, known as time dilation, means that distant cosmic events appear to unfold at a slower rate than they do locally. Some theories propose that as cosmic expansion accelerates, time itself could be affected in ways we have yet to fully comprehend. In one scenario, the continued expansion could eventually lead to the big freeze or heat death of the universe, a state where all stars burn out, galaxies drift apart, and the universe becomes a cold, dark expanse. In such a future, with no stars to mark the passage of time, the very concept of time could lose meaning. If no physical processes occur, time might, in a sense, cease to exist. General relativity suggests that time is not an absolute quantity, but a relative one, influenced by gravitational fields and motion. For example, clocks tick more slowly near massive objects, such as black holes, due to their intense gravitational pull, a phenomenon known as gravitational time dilation, which has been experimentally confirmed. Could something similar occur on a cosmic scale, with the expansion of space influencing the passage of time? While dark energy's effects on time remain uncertain, its role in shaping the universe's future is an open question in physics. Most discussions of cosmic expansion focus on large scales, but what about the smaller realms of physics? Does the universe's expansion affect the quantum world, where fundamental particles such as electrons and protons exist? At its core, Cosmic expansion increases the space between galaxies and galaxy clusters. However, within galaxies, and especially within smaller structures like stars, planets, and atoms, expansion has no noticeable effect. The forces that bind these objects, such as gravity, electromagnetism, and the strong nuclear force, are vastly stronger than the influence of cosmic expansion. On quantum scales, particles are held together by fundamental forces, such as the electromagnetic attraction between electrons and protons, or the strong nuclear force that binds quarks inside protons and neutrons. These forces are immensely powerful compared to cosmic expansion, ensuring that atoms, molecules, and even large objects remain unaffected. However, there may still be connections between cosmic expansion and quantum physics. Some theories suggest that quantum fluctuations in empty space played a crucial role in the universe's early inflationary period, influencing the formation of galaxies and cosmic structures. Additionally, if dark energy has quantum origins, the link between quantum physics and the expanding universe could be deeper than we currently understand. Ultimately, while cosmic expansion shapes the large-scale universe, it has little impact on the fundamental building blocks of matter. The universe grows ever larger, but the small-scale fabric of reality remains bound by the fundamental forces that govern it. The randomness in a system within the universe tends to increase over time due to entropy, meaning that systems become progressively more disordered. When a system reaches its highest possible entropy, no energy remains available to drive change or sustain processes. For example, the heat produced by stars is a form of usable energy, but as the universe expands, this energy disperses, becoming less concentrated and less capable of powering phenomena like stars or galaxies. The concept of heat death arises from this principle of increasing entropy. As the universe continues to expand, galaxies drift apart, and stars gradually deplete their nuclear fuel over billions and trillions of years. Eventually, stars will burn out, and either collapse into black holes, fade into cold white dwarfs, or explode as supernovae. With no new energy sources, these stellar remnants will cool and darken, leading to a universe with decreasing activity. In the distant future, the Milky Way and its neighboring galaxies in the local group may merge, but beyond that, other galaxies will become unreachable as the universe expands at speeds exceeding the speed of light. This will result in a universe that is increasingly empty, with isolated pockets of matter surrounded by vast expanses of void. Eventually, the only remaining sources of energy will be the faint radiation lingering from the Big Bang, and occasional emissions from decaying black holes. According to the heat death scenario, black holes will ultimately evaporate due to a process known as Hawking radiation. Predicted by physicist Stephen Hawking, this process suggests that black holes gradually lose mass by emitting minuscule amounts of radiation over vast timescales. While black holes may seem eternal, even the largest ones will eventually dissipate, leaving behind only low-energy particles. Once all black holes have evaporated, and all matter has decayed into its most fundamental components, the universe will be a cold, dark, and empty expanse. This state, sometimes referred to as the Big Freeze, marks a point where maximum entropy has been reached, with energy evenly distributed to the extent that no processes such as star formation, chemical reactions, or atomic movement can occur. In this state, the universe would be effectively lifeless, with no further activity taking place. It is important to note that the heat death of the universe is just one potential outcome based on our current understanding of cosmic expansion, dark energy, and thermodynamics. If the universe continues expanding indefinitely and dark energy remains constant, the heat death scenario becomes a strong possibility. However, many aspects of cosmology remain uncertain, and new discoveries could alter our understanding of the universe's long-term fate. One crucial factor driving the universe toward heat death is the role of dark energy. If dark energy continues to dominate the universe's evolution, it could prevent the formation of new structures, ensuring that the universe ultimately becomes a cold, expanding void. While this scenario may seem bleak, it is essential to recognize that the timescale for heat death is incredibly long, trillions upon trillions of years, making it difficult to fathom. For now, the universe remains in a relatively active phase, with stars forming, galaxies colliding, and life existing in various pockets of the cosmos. The heat death scenario represents a distant future, far beyond the lifespan of our solar system, Earth, or even the Milky Way galaxy. The idea of an ever-expanding universe is already extraordinary, but an even more dramatic possibility exists: the Big Rip. Unlike the slow cooling and fading associated with the heat death scenario, the Big Rip envisions a much more sudden and violent end to the cosmos. In this hypothesis, the expansion of the universe does not simply continue at its current rate, it accelerates until the very fabric of space-time is torn apart. The Big Rip scenario originates from observations showing that the universe's expansion is speeding up, a phenomenon primarily attributed to dark energy. While dark energy currently exerts a relatively mild effect, gradually pulling galaxies apart, the Big Rip hypothesis suggests that dark energy could become increasingly powerful over time. If dark energy strengthens, it could drive the universe's expansion to such an extreme that it overcomes even the fundamental forces holding matter together. Initially, this expansion would be evident on the largest scales, as galaxy clusters, normally bound by gravity, begin to drift apart faster than the speed of light, cutting off entire regions of the universe from one another. As expansion accelerates, galaxies themselves would unravel, with gravitational forces no longer sufficient to hold stars in orbit. Stars would be flung into the void as galaxies disintegrate. However, the Big Rip does not stop there. As the acceleration continues, even smaller structures like solar systems would succumb. The force driving the expansion would overpower the gravity binding planets to their stars, causing them to be torn away. Eventually, even atomic forces would be overwhelmed, and individual atoms would be ripped apart, leaving behind a universe composed solely of isolated subatomic particles. In the final moments of the Big Rip, even spacetime itself would be disrupted, with the fundamental laws of physics ceasing to function. As expansion accelerates infinitely, the universe would tear itself apart entirely, leaving behind nothing. Unlike the heat death scenario, which unfolds over unimaginably long timescales, the Big Rip could occur relatively quickly in cosmic terms, potentially within 22 billion years if dark energy grows in strength. The Big Rip remains speculative, as the true nature of dark energy is still unknown. If dark energy remains constant, the Big Rip will not occur, and the universe will follow a slower path toward heat death. However, if dark energy strengthens, this catastrophic fate could become inevitable. Scientists continue to study cosmic expansion and dark energy to determine whether this dramatic end is a real possibility. The idea that we might be living in a simulation has gained traction in recent years, fueled by advancements in technology and computing. Philosopher Nick Bostrom proposed in 2001 that it is not only possible but likely that advanced civilizations could create highly sophisticated simulations within which the inhabitants, us, might remain unaware of their artificial existence. From this perspective, the expansion of the universe could be just one programmed feature within such a simulation. Much like how virtual reality environments generate space dynamically as users move, a simulated universe could be designed to expand according to predefined rules. The accelerating expansion we observe, attributed to dark energy, might simply be an element of this programmed reality. If the universe behaves as a simulation, its expansion might not be a consequence of fundamental physics, but instead a function of computational parameters. Another perspective suggests that cosmic phenomena, such as dark energy's mysterious behavior, could be glitches or anomalies in the simulation's programming. Just as errors occur in computer simulations, inexplicable aspects of our universe, like dark energy's increasing influence, might reflect limitations or quirks in the underlying code governing our reality. While there is no concrete evidence to support the simulation hypothesis, it remains an intriguing framework for reinterpreting cosmic expansion. Whether our universe is governed by physical laws or an artificial system, understanding its expansion continues to be one of the greatest scientific challenges of our time. In unforeseen ways, space-time could form bubbles that behave distinctly from the surrounding cosmos. These pockets of space-time, influenced by exotic matter or energy, might either expand at an accelerated rate or collapse inward. This could result in extraordinary phenomena, such as the emergence of multiple universes within our own. If such theories hold true, the expansion of the universe may be far more intricate than a simple, uniform process. Instead, it might involve regions of exotic matter and energy that shape the cosmos in ways beyond our current ability to observe. If exotic energy does exist, there's a possibility that it could be harnessed in the future to manipulate or even reverse this universe's expansion. While this concept remains speculative, some researchers have contemplated whether it might one day be feasible to control space's expansion. If humanity were able to interact with dark energy or other unknown forces, it could lead to technological advancements capable of expanding or contracting regions of space at will, potentially unlocking groundbreaking opportunities for future civilizations. For instance, if a method were discovered to locally influence the rate of expansion, it could revolutionize space travel or even facilitate the creation of isolated space-time regions with unique physical properties. The question of how the universe will ultimately evolve remains one of the most profound in science, with multiple theories proposed to explain its fate. All of these scenarios hinge on how the universe's expansion progresses and what it means for matter, energy, and fundamental forces. Whether the universe continues expanding indefinitely, reaches a halt, or reverses course, its destiny is shaped by this cosmic growth. Beyond the well-known Big Freeze and Big Rip scenarios, another possible outcome is the Big Crunch. This hypothesis suggests that if the universe contains enough matter and energy, gravity could eventually overpower the force driving expansion. If this were to happen, the expansion would slow and eventually reverse, causing galaxies, stars, and planets to draw closer until everything collapses into an extremely dense state, essentially a reversal of the Big Bang. Though current observations suggest the universe's expansion is accelerating, making the Big Crunch unlikely, this scenario remains possible if the nature of dark energy changes over time. Another even more unsettling possibility is the concept of vacuum decay, rooted in quantum mechanics. This theory suggests that the universe exists in a false vacuum, an unstable energy state that could suddenly transition to a more stable one due to a quantum fluctuation. If this occurred, a bubble of true vacuum would expand at the speed of light, annihilating everything in its path and effectively ending the universe as we know it. This event could happen without warning, making it one of the most unpredictable and dramatic possible endings for our cosmos. Some speculative theories also explore the role of the multiverse in the universe's fate. Certain ideas propose that black holes might serve as gateways to other universes, and as our universe decays, new ones could emerge. In this view, while individual universes may have finite lifespans, the multiverse itself could persist indefinitely, cycling through endless creation and destruction. If the universe ultimately reaches a cold, stretched out state, often referred to as the Big Freeze or heat death, a key question arises. Could life still persist in such an environment? At present, life as we know it relies on stars as sources of energy, with sunlight powering ecosystems and sustaining habitable conditions on planets. However, in a universe where stars have long since burned out and temperatures approach absolute zero, alternative energy sources would be essential for survival. One potential source of energy could be black holes, which remain long after stars have vanished. Some theories suggest that matter falling into a black hole can release immense amounts of energy, which might be harnessed by advanced civilizations as a power source in a darkening universe. Another possibility is that life could adapt to extreme conditions by evolving to survive on minimal energy. On Earth, we already observe extremophils, organisms that thrive in extreme environments such as deep-sea vents, freezing polar regions, or highly radioactive areas. If life on Earth can survive in such hostile conditions, it is conceivable that in a distant, dying universe, new life forms might emerge that require significantly less energy to function. Moreover, intelligent civilizations could develop technologies to extend their existence, such as constructing artificial environments that preserve heat and energy. They might also slow their metabolic processes to minimize energy consumption, stretching out their lifespans as much as possible. Some radical theories even suggest that life could transition into purely informational or digital forms, existing in a quantum or computational state rather than a biological one. If multiverse theories are correct, there is also the possibility that life could escape this universe entirely, seeking refuge in alternate universes with more favorable conditions. If civilizations one day discover ways to traverse between universes, they might avoid the inevitable fate of our own. One of the most significant consequences of ongoing cosmic expansion will be the increasing difficulty of communication across vast distances. Although galaxies are relatively close to one another today, the relentless stretching of space will eventually push them so far apart that communication, whether through radio waves, electromagnetic signals, or even advanced unknown methods, will become impossible. As the universe expands, galaxies beyond a certain point will fade from view and recede beyond the cosmic horizon, making them permanently unreachable. Civilizations, if they exist in distant galaxies, will become completely isolated from one another, unable to exchange knowledge or resources. This means that any potential intergalactic networks, trade, or shared scientific advancements would eventually cease, forcing civilizations to rely solely on their own local galaxy for survival and progress. Even the most advanced communication technologies would be bound by the limitations imposed by the speed of light and the accelerating expansion of space. No signal, no matter how powerful, could overcome this growing divide. Within gravitationally bound galaxy clusters, civilizations could still interact, but beyond those clusters, the universe would become a series of disconnected cosmic islands. Black holes, among the most enigmatic objects in the universe, will play a crucial role in its far future. As cosmic expansion continues and galaxies drift apart, the supply of matter that fuels black holes will gradually diminish. Over time, black holes will cease growing, remaining as the last significant structures in an otherwise empty universe. Despite the cooling and spreading of the cosmos, black holes will endure for an extraordinarily long time. While stars burn out and galaxies fade, supermassive black holes at the centers of galaxies could persist for trillions of years before they eventually evaporate via Hawking radiation, a process so slow that the largest black holes may outlast nearly everything else in existence. For the final civilizations, black holes may become invaluable sources of energy. One proposed method of energy extraction is the Penrose process, which allows for energy to be harnessed from a black hole's rotation. Additionally, accretion disks, the swirling matter spiraling into black holes, could release enormous amounts of radiation, potentially sustaining advanced life for long periods. Some theories even suggest that civilizations could use black holes to slow down time relative to the rest of the universe, prolonging their existence in a gradually dying cosmos. In such a scenario, black holes could serve as sanctuaries for the last remnants of intelligence and complexity in an otherwise entropic universe. To answer these deep questions, humanity must develop far more advanced observational tools than those currently available. Modern telescopes have provided invaluable insights into cosmic expansion, but future instruments will push our understanding even further. The James Webb Space Telescope, JWST for instance, was designed as the successor to the Hubble Space Telescope, and offers unprecedented capabilities for studying the distant past and future of the universe. However, even more powerful telescopes and observatories will be necessary to unlock the remaining mysteries of cosmic expansion. By continuing to study the universe's evolution, we may one day uncover ways to manipulate cosmic forces, or at least find clues about the ultimate fate of everything. Whether our universe ends in an eternal freeze, a sudden collapse, or transitions into something entirely new, the quest to understand its destiny remains one of the most profound scientific endeavors of all time. The James Webb Space Telescope, JWST, was designed to detect infrared light, enabling it to peer further back in time than ever before. As the universe expands, light from distant galaxies stretches into longer infrared wavelengths. JWST is optimized to capture this light, offering scientists a clearer picture of galaxies that formed just a few 100 million years after the Big Bang. By studying these ancient galaxies, researchers gain insight into the early expansion of the universe and how that process has evolved over time. The European Space Agency, ESA, is also contributing to the study of cosmic expansion through missions such as the Euclid Space Telescope. Euclid is specifically built to investigate dark energy and dark matter, two of the most enigmatic components of the universe. Dark energy is believed to be responsible for the accelerating expansion of the cosmos, yet it remains poorly understood. Euclid's mission is to map the universe's geometry by tracking the distribution of galaxies and galaxy clusters over time. By constructing this large-scale cosmic map, scientists aim to uncover how dark energy influences the expansion of the universe. Euclid's observations may provide new clues about the nature of this mysterious force and its role in shaping cosmic evolution. Another groundbreaking initiative is the Square Kilometer Array, SKA, an international project to construct the world's most powerful radio telescope. Unlike traditional optical telescopes, the SKA will use radio waves to study the universe, allowing it to detect signals from some of the most distant objects ever observed. Since radio waves are less affected by cosmic dust, SKA will be able to peer through regions that are obscured to other types of telescopes. With a vast network of antennas spanning multiple continents, the SKA will gather incredibly detailed data on distant galaxies, the cosmic microwave background radiation, and the large-scale structure of the universe. These observations will help scientists better understand how cosmic expansion has influenced the distribution of matter and energy across the cosmos. The study of cosmic expansion isn't limited to observing galaxies. The next generation of gravitational wave detectors is expected to provide new insights into how the universe is evolving. Gravitational waves, ripples in space-time caused by violent cosmic events such as black hole collisions, travel across the universe, carrying information about its fundamental structure. Future instruments, like the Laser Interferometer Space Antenna, LISA, will be far more sensitive than current detectors, enabling scientists to analyze gravitational waves in greater detail. Because these waves are not influenced by light or matter, they provide a unique perspective on cosmic expansion, allowing researchers to explore space on both large and small scales. Breakthroughs in data analysis and computer simulations are also revolutionizing the study of the expanding universe. With modern telescopes generating enormous amounts of data, artificial intelligence, AI, and machine learning are becoming essential tools for processing and interpreting this information. AI algorithms are being trained to detect patterns, track the movement of galaxies, and make predictions about cosmic structures. This technology is particularly valuable in studying dark energy and cosmic expansion, as it allows scientists to test different models and refine their understanding of how the universe has evolved over billions of years. Future missions, aimed at studying the cosmic microwave background, CMB, will also be crucial in uncovering details about the universe's early expansion. Telescopes like the Planck satellite have already provided high-resolution maps of the CMB, revealing subtle fluctuations that led to the formation of galaxies and galaxy clusters. However, upcoming missions will refine these measurements even further, offering deeper insights into cosmic inflation, the rapid expansion that occurred immediately after the Big Bang. Ground-based telescopes, such as the Vera C. Rubin Observatory, will play a key role in surveying the sky with unprecedented depth and precision. By continuously scanning vast regions of space, the Rubin Observatory will track the motion of millions of galaxies, providing extensive data on the large-scale structure of the universe. This observatory will also enhance our understanding of dark energy by observing how galaxies and supernovae shift over time. Additionally, its ability to monitor the sky in real time will allow astronomers to detect unexpected cosmic events, offering new opportunities to study phenomena related to cosmic expansion. Cosmic expansion raises some of the most profound questions about the nature of reality, time, and space. While scientific advancements have provided a clearer picture of how the universe expands and how we can observe it, the fundamental cause of expansion remains a mystery. For instance, we know that distant galaxies are moving away from us and that this movement is accelerating due to dark energy. However, the true nature of dark energy itself remains one of the greatest unsolved mysteries in modern physics. Is it a force? A field? A property of space itself? And why did it start dominating cosmic expansion at a particular point in time? These questions challenge our deepest understanding of the universe. Additionally, the cosmological horizon places limits on what we can observe. Much of the universe lies forever beyond our reach, as its light will never have time to reach us due to the ongoing expansion. This raises a difficult question. Can we ever know what exists beyond our observable universe? Or are these regions destined to remain hidden forever? Even within the portion of the universe we can observe, the complexities of cosmic expansion might be too vast for human comprehension. Theoretical physicists rely on intricate equations to describe how space expands, how galaxies evolve, and how dark energy influences these processes. But there is a difference between mathematically describing a phenomenon and truly understanding it. We can accurately predict how galaxies will behave over billions of years, yet we remain uncertain about the underlying reasons behind these behaviors. Our human perception and reasoning are shaped by everyday experiences, where time moves in a linear fashion, space is relatively stable, and natural forces behave predictably. However, cosmic expansion challenges all of these assumptions. On the larger scales, time itself may behave differently, and the concept of an infinite yet expanding universe defies human intuition. Our brains are not naturally equipped to grasp four-dimensional space-time or the idea that the universe could be infinite while still expanding. These abstract concepts push the limits of what we can mentally process. Some scientists speculate that there may always be aspects of the universe beyond human understanding, not because we lack the right tools, but because the cosmos might simply be too complex for our cognition to fully grasp. While we can observe the effects of cosmic expansion, the deeper reality behind it may remain unknowable. Despite these challenges, scientific exploration continues to push boundaries. Not long ago, the concept of an expanding universe was unimaginable, yet today it is a fundamental part of modern cosmology. Whether the mysteries of dark energy and cosmic expansion will always remain unsolved, or whether the next breakthrough is just around the corner, is still an open question. What do you think? Could we ever fully comprehend the expansion of the universe, or will some aspects always remain a mystery? Let us know in the comments below. And if you enjoyed this discussion, consider liking and subscribing for more fascinating explorations of the cosmos. Thanks for watching.